In the previous module, we discussed how we need a Python development environment and an editor to get started with the Quantum Inspire SDKs. In this module, we want to show how to create and run a quantum computing algorithm on the Quantum Inspire backends. Algorithms on the Quantum Inspire platform are written in version 3.0 of CQASM, commonly known as Common Quantum Assembly Language. This is the language we would normally use in our web application. In the SDKs, however, we want to use our Qiskit or PennyLane plugins. In this module, we will use Qiskit. We learn how to connect to Quantum Inspire and how to select a backend to run an algorithm on. When the algorithm has run successfully, we inspect and print the results. At the end, we will provide a technical demo to showcase these steps. First, let's discuss what generic steps we have to take when we want to create and run our first algorithm via the Qiskit SDK. The core of the SDK is the API, short for Application Programming Interface. The API defines the interface to Quantum Inspire. It hides all kinds of technical details for us to interact with Quantum Inspire. We only need to take a few generic steps to run our first algorithm. First, initialize the Quantum Inspire API. Second, we select a backend for running our algorithm. And third, we run our algorithm on the selected backend. Finally, we can inspect the results. Let's take a close look at each step for running simple Bell state algorithm written in Qiskit. Qiskit uses provider instances to discover backends. As you might expect, the Qiskit Quantum Inspire SDK comprises a provider for the Quantum Inspire platform, called the QI provider. When instantiating this provider, the credentials stored by the QI after login are read and used to collect all backends provided by QI. We can use this provider to retrieve and to show all available backends. The provider instance we initialized in the previous step can be used to get backends from Quantum Inspire. To actually run the algorithm, we have to select the backend we want to use. For this, we use the method getBackend. In the example below, we select the QX emulator. This is a quantum emulator backend which can simulate algorithms using up to 26 qubits. Next to the simulator backend, we have two hardware platforms which can be used. These backends are called Starman5 and Spin2+. They have a fixed number of 5 and 2 qubits respectively and slightly reduced primitive gate instruction set. Using Qiskit, we can create a quantum algorithm by defining function calls on a quantum circuit object. Every function adds an instruction to the circuit. When we are satisfied with the circuit, we can call run on the backend we specified in the previous step. One of the parameters of this method is shots. This is the number of times we want this algorithm to run. Run the algorithm more often to get a probability distribution of the results. If this is not specified, we use the default shots value of the backend. In this case, this is 1024. Obviously, the higher the number, the longer it will take to run the algorithms. When the algorithm is scheduled and runs successfully, we get back the result. You can ignore the message that the experiment cannot be optimized and may take longer to execute. Some algorithms can be optimized for simulators and run much faster. In this case, the algorithm is not optimized and it can take a while before the results appear. This probably will take a minute or so, or even longer when more algorithms of other users are scheduled simultaneously. The result value returned from Quantum Inspire is a dictionary containing multiple fields. One of them is called data and represents a histogram. This histogram contains the different states and their probabilities. Because this is a Bell state, we expect the result to be around 50% for both states 00 and 11. The state represents the measured values of qubits, where qubit 0 is the most right value and qubit 1 the most left. In case of Qiskit, the qubit state is hexadecimal encoded. This means that 00 is represented by 0x0 and 11 is represented by 0x3. Another interesting field is system message. On the slide, it's empty. This is because the circuit was executed successfully. If the circuit had failed, the dictionary would be filled with an error message and a trace ID, amongst others. The message would explain what went wrong. If you want to know more about the error, you can use the provided trace ID when contacting the support team of Quantum Inspire. With this trace ID, we can easily find the original error in our logs. After running a circuit, we can also find the job and results in the Quantum Inspire web interface. To do this, we have to log into the Quantum Inspire website using the same account as we used to run our algorithm. On the landing page, we see an overview of our projects, including the project with the name Program Created by SDK. When we open this project by selecting it, we get into the editor with our source code. job, and result in the sidebar. The result will have the name results with an ID behind it. Every result gets a unique ID suffix. When we click on this result, we see a visualization of the histogram we printed earlier. When we click on the source code, we can also see a graphic visualization of our circuit. Here we see the information we get back from the API method getBackend. The Starman 7 backend is a hardware backend. For hardware backends, the topology of the qubits is defined in the field coupling map. The topology defines for each qubit to which qubit they are connected. These edges are unidirectional. In this case, we would see qubit 2 is connected to qubits 0 and 5, qubit 3 is connected to qubits 0, 5, 1, and 6, and qubit 4 is connected to qubits 1 and 6. Important to know is that for the Starman 5 topology, we only use 2 qubits gates on qubits that are connected. The consequence of this is that our example program won't run on the Starman chip because we use a CNOT gate on qubit 0 and 1, which are not connected. We can rewrite the algorithm to use qubit 0 and qubit 2 instead. Field status indicates the status of the backend. This field is currently not implemented. If a backend is reported to be busy, which means it's either in the executing or calibrating state, we can still send in a job and it will be added to a queue of pending jobs. When the backend status is offline, this means the backend is not available for executing experiments. The field operation names defines the subset of CQASM operations that is supported by the backend. Field max shots defines the maximum number of shots that the backend allows. The number of shots is a parameter for the backend method run as we saw earlier. If this number exceeds the maximum number of shots, the number of shots is automatically capped to the max number of shots. So in the previous demo, we showed you how to get your Python environment ready by installing the needed packages and installing the CLI tool, which you need to log in. In this demo, we will jump into how we can use the Qiskit plugin to define a circuit and run it against one of the Quantum Inspire backends. To get started, let's make sure we're logged in. So what I'm going to do, I'm going to go to a terminal and run the QI login command that was shown in the previous demo. This should redirect us to the browser where we can confirm our login. All right. I'm going to close these two. So this means our login credentials have been updated and we can go about talking to the API. So I'm in the Jupyter lab, just as shown in the previous demo, and I'm quickly going to confirm that we have the needed packages installed. I'm going to open a terminal. And I'm going to list all the pip packages that have been installed that have something to do with Quantum Inspire. So we should see the Qiskit plugin in here, and as you can see, it's right there. And the nice thing about this package is that it also installs Qiskit itself for you. So if you would check which Qiskit packages are installed, as you can see, these are all installed and we can go about using them. So this is all the preparation needed. Let's try to build a circuit using Qiskit and try to run it against one of the Quantum Inspire backends. First of all, we're going to import quantum circuits from Qiskit. This is a standard way for Qiskit to define quantum circuits. And what you do is you create one of those quantum circuits and then apply certain functions to it to define an algorithm. And that's what we do right here. This is a simple Bell state. And we're going to create this circuit by simply running this cell. As you can see, it was created. So next, what we actually want to do, we want to get a QI backend. And to do this, we're going to need a QI provider. So from Qiskit Quantum Inspire .QI provider, which is this one, we're going to import the QI provider. Just like that. And since our package is installed, this should just run fine. And we can use this QI provider, or at least an instance of it. So the first thing we're going to do is initialize it. This QI provider. Let me quickly run this one. And this provider allows us the ability to check which backends are available. So we're going to have a look at how to do that. Provider.backends. And this should return us a list of all available backends, as you can see below. Now that we have listed all the backends, let's select one of them and get started. For this example, I'm going to select the QX emulator backend. So I'm going to copy over the name. I'm simply going to call the provider.getBackend method. Provide a name. And let's store this in a variable named backend. If I were to debug this and have a look at the variable backend, you can see that a lot of additional information about the backend is provided, like the max number of shots or the number of qubits. I'm going to create a new cell, and now we're going to run our circuit on this backend. So to do this, we simply call backend.run, and we provide the circuit. You could additionally provide the max number of shots, which I'm not going to do here, so it's going to take the default value or the max value for the backend, which is 2048. Since this is an emulator, this shouldn't really matter too much in performance. I'm going to store this as a job, because what we're sending to the QI now is a job to run the circuit. This could be done immediately, but if there are many queued circuits already or many queued algorithms, this can take a while. So we've stored the job now, and now we can simply get our results by calling job.results, like so. And let's store this as a result. All right. So now we can print this result and have a look at it. As you can see, there are multiple values, multiple fields that are included in the result. But as you can see here, we have the data, which is a representation of the histogram, like we discussed earlier. And if everything went right, we should be able to go to the editor now, do a refresh. As you can see, there's a new project called Program Created by SDK, which name you could change, by the way. But if we look into the code now, we see that the exact Bell state that we defined earlier using Qiskit was translated to CQASM and can be found here. We can also see a visual representation of our algorithm, and we can have a look at the results as a histogram. And this makes sense since we kind of expect a 50-50 distribution for this specific algorithm. That's it for this demo, and in the next demo we're going to have a look at hybrid algorithms. This concludes our video about QI SDK basics. We learned how to run an algorithm on a quantum-inspired backend using the Qiskit SDK. We saw we had to initialize the provider first. We used this provider to select the backend to run our algorithm on, and then we executed the algorithm. We used the Qiskit quantum circuit to build our circuit. After the algorithm runs, we inspected the results and printed the histogram. We were also able to look up the project on the Quantum Inspire website. At the end, we looked at some properties of a Quantum Inspire hardware backend and how we can use it in our programs.